Mosul Dam rises 370 feet or 113 meters above the Tigris River in northern Iraq as one of the tallest dams in the Middle East. The dam was built in the 1980s, but in a way, construction never really stopped. That's because ever since the reservoir filled behind Mosul Dam, the ground has literally been dissolving non-stop below the structure. Almost immediately on filling, water started flowing through the foundation of the dam and back out on the downstream side. Just a year later, the volume of seepage was measured at 800 liters, or about 200 gallons per second. I usually hate to use the Olympic-sized swimming pool equivalent, but in this case it makes sense because it was enough to fill one every hour of every day. And the issue is that once a process like that gets started, it's pretty hard to stop. So, for the past 40 years or so, the problem at Mosul Dam has been ongoing, scrutinized by some of the most preeminent engineers across the world, and complicated by politics, bureaucracy, and of course, armed conflict. Failure of a structure this large would be catastrophic. Towns along the Tigris River would be fully wiped off the map, and some estimate that the breach wave would be so massive that even major parts of Baghdad, hundreds of miles downstream, would be submerged. In 2006, the US Army Corps of Engineers called it unequivocally the most dangerous dam in the world. That was 20 years ago, and Mosul Dam is still standing, in better shape than ever, and the story of how it got there is fascinating. I'm Grady, and this is Practical Engineering. Mosul Dam is an earthen embankment dam not far from the city of Mosul in Iraq, built to generate hydropower and store water for irrigation and drinking. The hydro plant is on the west side of the dam with 4 turbine generators. You can see the massive surge tanks sticking up from the plant that absorb changes in pressure when the units are started and stopped. The dam has an outlet structure through the embankment here. It has a service spillway with radial gates here, and an auxiliary spillway with earthen fuse plugs here. Check out my videos on spillway gates and fuse plugs if you want to learn more about those types of structures after this. The dam itself is impressive, but the rock that serves as its foundation is extremely complex, and in many ways, far from ideal. The geology of northern Iraq includes a lot of gypsum, a sedimentary rock that's widely used for things like fertilizer, plaster, and drywall. What it's not widely used for is the foundations of dams. In fact, the consensus of experts involved on Mosul Dam throughout the years is that it was all around a terrible idea. One consulting group said that, quote, "The decision to locate such a major and important dam on the foundation rock mass which exists at the Mosul Dam site was fundamentally flawed." That's because of a critical property of gypsum, one that it doesn't share with many other types of rock formations. It dissolves in water. You might be familiar with limestone caves and karst geology, where water creates voids in the subsurface. Some of these can be quite dramatic, like Carlsbad Caverns in New Mexico or Mammoth Cave in Kentucky. They're formed because the limestone is just a tiny bit soluble in water, as long as it's a bit acidic, which rainwater usually is. So over the course of millions of years, that water kind of carves away the earth from the inside. Gypsum, on the other hand, is roughly 200 times more soluble in water than limestone. It's not quite like a spoonful of sugar or salt that dissolves almost instantly, but processes that usually take centuries in limestone are accelerated to human timescales in gypsum. And that's especially true in the subsurface because dissolution isn't a linear process. More dissolving means more space for water, which means more dissolving, and so on. It's a positive feedback loop. Many dam failures have resulted from internal erosion, where water seeping through the soil or rock carries away particles, leaving voids. This process is what led to the demise of Teton Dam, which I covered in an earlier video. But where internal erosion can be combated by designing filtration systems that catch waterborne particles before they escape the subsurface, you can't easily filter dissolved gypsum out of seepage. The designers of the dam knew that gypsum was going to be an issue, and they had a few ideas to address it. One was to install a blanket of bentonite clay lining the bottom part of the reservoir. This would block seepage from flowing into the subsurface, at least in the dam's immediate vicinity, lengthening the flow paths and thus reducing the total volume of flow. However, the volume of material would be enormous, and the blanket layer would be fairly fragile to damage from boats or even strong currents. Another idea was to use a cutoff wall, basically a continuous subsurface diaphragm of some impervious material. The problem was that there were no machines that could trench deep enough to get below the worst of the gypsum. The idea they landed on was the same as at Teton Dam, a grout curtain. Mosul Dam's design included a continuous concrete tunnel running along the bottom of the structure. It had one purpose: to provide access to the dam's foundation for drilling rigs and grout pumps. Political and schedule pressures pushed the government to finish the dam before the grouting was complete, but they knew they would have access to the gallery tunnel to continue that process after the dam was in operation. Unfortunately, they underestimated how serious and complex a challenge they were setting themselves up to face. As soon as the reservoir filled up, the problem became obvious. I mentioned the Olympic swimming pools of seepage in the intro, but it wasn't just that. Sinkholes opened up downstream of the dam as caverns formed in the geology below, causing the surface to collapse. As time went on, those sinkholes started appearing closer to the dam, an above-ground hint at how the solution cavities were migrating in the subsurface. Essentially, since its construction, operators have maintained a continuous grouting program, injecting a mixture of sand, cement, bentonite, and water into the rock below through drilled holes to try and plug up the voids. It's basically a non-stop race between logistics and chemistry, because grout doesn't fare well in flowing water and the foundation rock is constantly dissolving. Recognizing the hazard they had created in the 1980s, the Iraqi government came up with a backup solution. Since it was clear that there was really no permanent fix for Mosul Dam, they would just build another dam downstream that would capture the flood if and maybe when Mosul Dam failed. Badouche Dam started construction in the late 1980s. It would have a hydropower plant and store water for irrigation, but also include a huge empty storage pool to protect downstream cities from a breach of Mosul Dam. The project got about halfway finished before the geopolitical situation in Iraq ground it to a halt. In 2003, a US-led coalition invaded Iraq as part of a larger war on terror in response to the September 11th attacks. As a major piece of infrastructure in the country, Mosul Dam had the coalition worried. Some early reports hinted that Iraqi forces might detonate the structure as an act of sabotage, but it didn't take long to realize that the dam might fail on its own accord. They started coordinating with the U.S. Army Corps of Engineers to assess the structure, whose report concluded that the risk was astronomical. That's the source of the "most dangerous dam in the world" quote that has plagued the structure ever since. The truth is that the danger of a dam is pretty complicated to characterize, and it's not a statistic that's widely tracked, especially at a global scale. But the fact that a government agency was willing to say it means a lot, and Iraq's Ministry of Water Resources took the situation seriously and started working with a panel of experts to review the conditions of the dam. That panel largely came to the same conclusion: Mosul Dam needed serious help. Coalition forces had bases and equipment along the Tigris River. The situation was concerning enough that they decided to move everything out of the potential inundation area if the dam were to breach. At the same time, a major part of the war effort was helping the new Iraqi government shore up the country's infrastructure, including improving the grouting program at Mosul Dam. Even though it was really only considered a temporary solution, the consensus seemed to be that it was the only feasible way to address the foundation problems beyond the stalled Badouche Dam project downstream. Initial efforts by the US government to help at Mosul Dam turned into somewhat of a disaster. A few notable examples: the winning contractor for the grout plant submitted a concrete, not grout, mixing plant design, and somehow the review committee didn't notice, despite it being printed on the front page of the submittal. By the time someone realized it, the concrete plants had already been delivered, and the US government had to pay the contractor to try and convert them into grout mixing plants. The material silos were poorly designed with no ladders or braces. Some weren't even bolted to the foundation. The loading ramp for the hoppers had no retaining walls, causing the slopes to slough off. Drills and pumping equipment couldn't even fit into the grouting galleries below the dam. And the dam operations staff meant to run all this new high-tech equipment had only received a few weeks of training. The oversight report about the project was scathing. Millions of dollars had been spent on 21 contracts for almost no benefit to the dam. Coalition forces continued efforts to improve the situation at Mosul Dam, but by 2010, the US was withdrawing troops from the country and handing off the reconstruction projects back to the Iraqi government. Unfortunately, that handoff was only temporary as sectarian violence continued to plague the region. In mid-2014, the Islamic State, also known as ISIS, ISIL, and Daesh, took over several cities in northern Iraq, disrupting the supplies of materials to Mosul Dam, which was still relying on nearly 24/7 grouting operations to keep the structure safe. That August, ISIS seized control of Mosul Dam, sparking new fears that the structure would collapse. For more than a week, the dam was out of the hands of the Iraqi government, and no one knew what the militants might do, or what they might not do. It was the same situation as before. Even short-term neglect presented a serious safety risk. Fortunately, the dam was recaptured by Kurdish and Iraqi forces with the help of US air support 8 days later. The dam was back in Iraqi hands, but the surrounding areas weren't. With equipment looted during the brief seizure, the disruption of the workforce at the dam, and without regular shipments of cement, the grouting operation wasn't being maintained. Equipment installed during the Iraq War wasn't being used, voids were going untreated, and concerns about the dam's failure continued to grow. Realizing that the Iraqi government was too fractured to manage the situation alone, the US decided to stay involved as Mosul Dam's de facto engineer. In 2015, the Army Corps of Engineers led a task force to assess the condition of the dam, and the results were alarming. The US Embassy released a fact sheet based on their findings, saying that the dam had an unprecedented risk of catastrophic failure, endangering between 500,000 and 1.5 million people along the Tigris River. A collapse would be a humanitarian crisis unlike almost anything in modern history. The situation was further complicated by the ongoing occupation by the Islamic State, making it difficult or impossible for residents to be able to evacuate to safer areas. Electrical blackouts, lack of government coordination, and poor communication would make things even worse in the event of a failure. The Iraqi government tried to downplay the alarm a bit. In an interview on TV, the Minister of Water Resources said, quote, "The looming danger to Mosul Dam is 1 in 1,000. This risk level is present in all the world's dams." I don't know if he made that number up or if it was actually supported by some kind of analysis, but anyone involved in risk management would find it hilarious if it weren't such a serious situation. Assuming that's an annual probability, which is what we normally use, and multiplying it by the consequences of failure estimated by the Corps of Engineers, you get an expected annual fatality rate of 500 to 1,500 people. Nowhere in the world would anyone consider that acceptable. This is a graph often used to communicate tolerable risks on large dam projects. This green area generally means there's not a lot of justification for making a structure safer. Yellow, you have to be more thoughtful. Red means unacceptable. Taking the minister's estimate of probability and the embassy's estimate of fatalities at face value, Mosul Dam would plot somewhere around here on the chart. That most dangerous dam in the world moniker doesn't seem like hyperbole when you look at it like that. To quote Lieutenant General Sean McFarland, "If this dam were in the United States, we would have drained the lake behind it." The urgency finally spurred action in 2016. Iraq awarded a contract to an Italian company to rehabilitate the structure, including a massive operation to expand the foundation grouting program. It was one of the most unique civil engineering projects on the globe, with participation from the Iraqi government, the US through the Corps of Engineers, the Italian military, and a number of international consultants. I actually talked with a few of the engineers involved on the project, and some of their stories are pretty wild. In the early days of the project, they were inserting engineers at night by helicopter to support the Iraqis who were operating the dam and install equipment that would let them monitor the situation remotely while ISIS was operating only a short distance away. The entire project had to happen near the front lines as the conflict with the Islamic State continued to unfold in Iraq. Security forces were needed for the entire duration to protect the dam and supply routes for materials and equipment. That took some time to get set up, but eventually the project team was able to establish a permanent camp at the dam. Over the next few years, all the grouting infrastructure, including batch plants, piping, electrical systems, and drill rigs, were replaced with modern equipment. Crews drilled more than 5,000 boreholes, with a total length of drilling at more than 400 kilometers, or 250 miles. 41,000 cubic meters, or 50,000 cubic yards of grout were injected into the foundation along the entire length of the dam. Generally, the way it works is this. You can inflate a rubber device called a packer using air or hydraulic pressure, creating a seal between the borehole and injection pipe. Or you can just grout the injection pipe directly into the borehole. Then you can pump grout at very high pressure into the borehole, forcing it into voids, cracks, and fissures. You just keep pumping until you reach a refusal criterion, a certain maximum pressure that you hold until the grout stops flowing. And you just keep doing it over and over and over. All this work was done using a sophisticated computer system to keep track of pressure, depth, mix design, flow rate, and quantity of grout for every borehole, allowing the team to track progress, identify issues, and visualize the performance of the operation. From material delivery to batching to drilling and injection, every step of the process became a data point. I love unique measurement units, and this project had a good one. As a quality control test, the contractor would try to inject water into the foundation rock after it was grouted up. Illusion is the loss of water of 1 liter per minute per meter of borehole length at an overpressure of 1 megapascal, or about 145 psi. For all the permeability tests performed for the project, 98% had values below 3 lugons, a massive improvement over the conditions beforehand. The project finished in 2019. It was a 3-year effort that cost more than $500 million, but Mosul Dam lost its most dangerous dam title as a result. By all accounts, the dam is in a much less precarious position. The project won an award from the Deep Foundations Institute in 2022, highlighting the complexity and the danger of the work. But this wasn't like a typical construction project because the work isn't over. The goal was to get the Iraqi government set up to continue the process of maintenance grouting. The rock below Mosul Dam may have a lot more grout than it used to, but the gypsum is still soluble, and there's still a massive reservoir constantly trying to push water through it. A major part of the rehabilitation project was training the Iraqi staff to continue the fight. In that way, despite its magnitude, the project was sort of a $500 million band-aid. The grouting has never been considered a permanent solution, and even though this project resulted in an enormous improvement in long-term prospects of the structure, it's still a major, ongoing obligation. Iraq is still planning for a more permanent fix. You can see the half-finished Badouche Dam on the map downstream from Mosul, and finishing the job is still on the table if anyone can figure out how to come up with the billions of dollars it would take. Another option is that deep foundation cutoff wall considered during the original design. It would provide a continuous barrier for seepage passing through the porous rock below the dam. These are used on a lot of dams across the world, but it's never been done on the scale and depth as would be required at Mosul. In 2018, the estimated cost for a cutoff was between $3 and $5 billion, an almost unimaginable investment into a dam that already exists and functions today. Whether the electricity and water from Mosul Dam is even worth that scale of capital is something that will probably take a long time to decide. Until then, the government will keep pumping grout and dinars into the rocks below in a non-stop race against a flawed foundation. but now with much more confidence that they can keep up the pace. One of the trickiest parts of Mosul Dam is that you can't just see what the subsurface looks like. The Army Corps of Engineers did a really detailed investigation, but even then, a lot of it is guesswork based on very limited observations from individual boreholes scattered across the site. This is a challenge for all kinds of engineering projects too, understanding the things we can't easily see. My friend Brian at the Real Engineering channel has a solution in his new series, The Anatomy of. He's putting everyday objects and devices into a CT scanner, so we can literally see inside. This is such a cool exploration of what makes up our favorite gadgets, and if you want to check it out, it's only available on Nebula. You probably know about Nebula now, even if you're not subscribed. It's a streaming service built by and for independent creators. No studio executives deciding what gets the green light, no advertisements driving the content into a single style. It's just independent creators making stuff they're excited about with as few barriers and distractions as possible between you and us. My videos go live on Nebula before they come out here, and my practical construction series was specifically produced for Nebula viewers who want to see deeper dives into specific topics. I know there are a lot of streaming platforms out there right now, and no one wants another monthly cost to keep track of, but I also know that if you're watching a show like this to the end, there is a ton of other stuff on Nebula that you're going to enjoy as well. So I've made it dead simple. Click the link below and you'll get 50% off an annual plan. Pay just one time, $30 for an entire year's access at go.nebula.tv/practicalengineering. Or if you have subscription fatigue but still want to support what I'm doing, you can get a lifetime membership. Pay once and have access for as long as you and Nebula last. If you're with me that independent creators are the future of great video, I hope you'll consider subscribing. Thank you for watching, and let me know what you think.